morning. Once again I welcome you to this lecture series on foundation engineering, and we have already completed a number of topics. For example, soil investigation, shallow foundation, deep foundation, retaining wall. And while discussing retaining wall, I have mentioned about different types of wall, and out of which we have only taken gravity retaining wall, cantilever retaining wall, and to some extent reinforced earth retaining wall. Just I have given taken introduced, but I have mentioned another type of wall, that was a sheet pile wall, and that was a particular application. And again in sheet pile wall also can be of different types. So, let me start with that sheet pile wall, and we can see that sheet pile walls consist of continuously interlocked pile segments embedded in soils to resist lateral pressure, and it is classified as a flexible retaining wall, and because it can resist a large amount of lateral deformation. So, if I typically if I show the elevation, it will be something like this, and it will be embedded here, and it is our ground original ground mark. So, if it is, so this is actually thin sheet like material, thin sheet, and the cross section of the sheet can be like this, can be like this, can be like this, or can be like this. So, these are the steel sheets, and there is interlocking. So, one after another can be connected, and one by one, and then laterally it can be extended, and it has a dimension actually depending on requirement. The depth will be also cut accordingly. So, this is seen actually cross section, and it is perpendicular to the port will be the elevation. So, this is the actually length suppose required. So, this will be embedded, but typically if I cut here, I may say this, I may see this, or I may see this, or I may say this. So, like that, if this is the ground mark and this is again ground mark, and if it is a thin sheet like this, then because of this pressure it will deflect something like this. Okay. So, that means in a normal retaining wall we do not allow that much deflection, but here it can undergo a large lateral deformation. So, that is the difference with normal regular retaining wall. So, this is the your sheet pile wall, typically cross section and other things, how it deforms. Now, let me see this one actually. See the applications, various applications, actually you can see the as continuous waterfront structure. So, like jetty and all that places, this sheet pile wall would be there. River bank protection. So, when there is a river bank to be protected, then the continuous sheet pile wall can be driven, and then that will help to resist the erosion. Then excavation and temporary supports in foundation with high groundwater table. So, when you want to do deep excavation particularly, then we can have this type of support, and then either temporary or permanent. And again these are the application, different type of application of retaining or sheet pile wall. And again this sheet pile wall again further can be classified in two ways, either it is cantilever or it is anchored. So, you can see here that this is the typical example of cantilever retaining wall. Cantilever, why it is called cantilever? Because it is the embedded portion, and this is the elevated portion. So, this is this much depth of soil, it is supporting by this wall, and there is no this portion, that means if I consider this is fixed, and this will bend like a cantilever beam. So, this why that is why it is called cantilever sheet pile wall. And if the deformation is because of this high excavation, if the deformation is too large, sometime to reduce the deformation, somewhere in between there will be anchored, and it will be gone inside, and by different ways this anchoring can be done. So, if it is this type of connection is given, then that is called anchored sheet pile wall, and this anchored sheet pile wall's purpose is to reduce the deformation. So, here actually if it is free, the deformation can be so much, and if you do this, then your deformation will be something like this. So, your top deformation will be reduced significantly. So, something like that it will have deformation. So, this is a different, that means cantilever and then anchored, and so this is the example of cantilever. Now, I will go to next, that is your anchored retaining wall, anchored sheet pile wall. You can see this is the typically anchored sheet pile wall. This is the sheet pile wall and this is anchored and by some means, and anchoring can be done in different ways, and you can see that is one dead weight can be kept here, or there can be a continuous wall can be built where it will be tied, or there can be some the batter pile, and then there will be some connection through this, it can be connected. So, this is different ways of anchoring. This is three different types of anchoring. In general, anchored means when that some from the ground level, below the ground level at some level, if it is connected to the sheet pile and it is anchored somewhere, then that is called anchored sheet pile. And what are the different ways of anchoring? This is one dead weight, this is the one by wall, and this is the one sometime batter pile connection here. Next, actually now as I have shown before that your retaining wall, flexible retaining wall, and you can see the deformation, typical deformation when it will be is a ground mark is here and it is a cantilever and this is embedded, then the wall typically rotate like this. If it rotates like this, then what happens? This portion is active and this portion is passive, and again this portion is active. So, these are the three different zones are there, and if you typically plot the pressure diagram, then you can see the pressure will be it will be active pressure diagram here, and then when you will go deeper, then because of the addition of the passive pressure it will become 0 somewhere, then it will become some value, and again this side again there will be some this side again passive value will be there. So, this will be this side is passive and this side active. So, here actually this side active, and here in this zone this side actually your passive and this side active, this side similarly here also just reverse. So, this is the typical pressure diagram, and you can see if the H is the cantilever portion, then you need to find out most important part in this cantilever retaining wall is to determine the how much depth of embedment is required. Okay. So, to find out that, so there are you can see here there are two parts from where actually your pressure becomes 0, from there to the end of this actually if you denote, if you say, and if I from here to here if I say y naught, the depth required will be d naught plus y naught, and this actually then we can that is one thing that you have to find out the depth of embedment, and similarly and at the same time the sheet pile wall actually thin actually depending upon your bending moment you have to choose the section. So, that is why that you have to find out also the bending moment. So, that part I may not discuss in length, mostly I will try to find out depth of embedment, that is the only part I will discuss in length. So, here you can see that d can be, so d actually a total embedment depth, and based on this pressure diagram I can show two parts, that is d naught actually from 0 where the pressure becomes 0 to the end, that is d naught, and from the dredge level to the where pressure becomes 0, that distance is suppose y naught. These two together actually your depth of embedment required, and once based on this calculation whatever depth of embedment will get, to have the definite factor of safety we can increase by 20 to 40%. So, that becomes the final depth of embedment. So, we can see here again when you have that cantilever sheet pile wall, Then from soil, actually the embedded zone, that is this is a zone and this is the retaining zone. So, two zones are there. So, this zone generally it has to be cohesionless, the sandy soil, and this portion, if it is sand is good, otherwise also it can be possible that it can be either sand or clay soil, clayey soil. So, that means you can have again different combination, sand continuously, sand here, then one type of analysis, then again sand here and cohesive soil here, then there will be analysis, will be another type of analysis. And if it is both places cohesive here, okay, that is also another type of analysis, but that is rarely used because this zone cohesive soil hardly will be used. So, we will not discuss in length, only I am telling you the different combination, that means only sand, okay, that is retained soil also sand, embedded soil also the soft sand. Retained soil is sand and embedment is done in suppose cohesive soil, then there will be another type of analysis. So, this is the typical pressure diagram. So, one by one actually you have to find out different parameter y naught. So, the different terms are shown here, P p double dash, P p bar, P p dash bar, and then these are the things we have to find out actually, and then based on that we can find out d naught. So, before going to d naught, let me find out the y naught, where actually y naught will be there, because your at this point actually 0, that means at point O, this is at point O, the passive pressure acting towards the right, passive pressure acting towards the right, that from here, and active pressure right should be equal to the active pressure acting towards the left. So, this side actually active pressure and this side actually passive pressure. So, this passive pressure and this active pressure must be equal. So, that is what we have done. If this depth at which your pressure becomes 0, if it is y naught, then gamma times y naught multiplied by K p is the passive pressure from here, and this side what is the active pressure? Active pressure will be up to this. So, H plus y naught, multiplied by gamma into K A. So, that become active pressure from the right, passive pressure from the left side, and this must be equal, because I am getting at this point 0. So, this if I equate, then I am getting a y naught. Y naught will be gamma h k a by gamma k p minus k a, and gamma h k a actually gamma get cancelled, and h k a gamma h k a is given as P a bar, that is the one P a bar, gamma h k a, and gamma k p minus k a is written as k, actually K p minus k is here nothing but K p minus K a. Okay. So, this that means if I can calculate what is the active earth pressure at this point, what is the active earth pressure at this point divided by gamma times K p minus K, if I do, then I get y naught, that is first parameter is obtained. Next part will be, you can see here, next part for the static equilibrium, that means if this is the pressure diagram and effective pressure diagram, actually this one you can see this is the pressure diagram, these are the final pressure diagram at this, because of this bending the pressure will be this side and then pressure. So, according to the bending shape of the wall, actually pressure diagram will be like this. So, we can say for static equilibrium that the sum of the all forces in horizontal direction from the left and right must be equal, and if I want to do that, then you can see that this entire thing is nothing but P a, this is P a minus half P p bar half p p bar this one, half p p bar d minus y naught, and total depth is d minus y naught. So, this portion I am taking this portion, I am taking this portion, and plus half plus this is plus and this will be plus and this is minus. So, p p a minus this plus half p p bar minus p p bar dash. So, this is actually p p bar dash plus p p bar this one. So, this area actually. Okay. So, that means I need to take this area, but I have taken this area, because of that I am now taking this area. So, that means twice, once plus and minus. So, this will be ultimately eliminated. So, this is the way it is done. So, you can see I have to take this area, I have to take this, I have to this area minus this area plus this area. So, what I have done, I have taken this area, I have subtracted this much area, that means I have subtracted this much more. So, what I have to do while adding this, now if I add this and this, then this is actually whatever subtracted, this will be again added. So, it will be balanced. So, this is the way the force equilibrium is done, and if you simplify, then it will H become p p bar, that means this one, d minus y naught minus 2 p a, that means this one area of this diagram, and divided by p p bar plus p p bar dash. P p bar dash is this one. So, this is the another expression of H we are getting, and H is shown here actually. That means, where actually this from the ground, where actually this from active to passive it is happening, that actually you have to find out. So, this is H we have calculated. Next part will be, next part actually you can take the moment with respect to the bottom of the pile. So, here actually if I take all forces, if I take moment here, and that must be also equal to 0, because there is no other external moment acting on it. So, you can see P A moment d naught plus y bar, d naught P A actually if I take. So, this is d naught plus y bar. So, suppose this area is acting somewhere, this resultant of this force is acting suppose somewhere here. So, P A multiplied by d naught plus y bar, and then a half P p bar this one d naught multiplied by d naught by 3. So, that 1/3 distance plus this force multiplied by h. So, this area and multiplied by h by 3. So, this is the moment taken from this, and if I simplify, then it become like this, and 6 p a d naught plus y bar minus p p bar d naught square plus p p bar plus p p dash bar h square. And now, p p bar, if I can say gamma h gamma k d naught, if I say p p bar equal to gamma k d naught, gamma k is here k a k p minus minus k a, k p minus k a, and p p dash bar will be nothing but p p double dash bar plus gamma h k naught. So, that means, p p double dash is this one, you have to find out this one. So, if I express this one by this and this one by this, and if I substitute all in this, then further it will be simplified to a form. You can see it will be modified, or it will be reduced to actually you have to substitute those and then simplify, and that can be again finally written in this simple equation form, and where d is the function, d naught is the function, and C 1, C 2, C 3 and C 4 are 4 constants. So, what is C 1 actually? C 1 is actually p p double dash bar by gamma k, C 2 is minus 8 p a by gamma k, C 3 is minus 6 p a gamma k square, 2 y bar gamma k plus p p double dash bar, and C4 equal to minus 6 P A y bar P P double dash bar plus 4 P A square by gamma. So, everything what is what it is shown in this diagram. Accordingly, you can calculate, and then that means you can calculate coefficient C 1 by this, coefficient C 2 by this, coefficient C 3 by this, coefficient C 4 by this, and then put this in this equation, and then this equation will be a equation of d naught of fourth order equation of d naught. Then this equation actually can be solved different ways in the exam, or for solving depth of the foundation depth of the embedment here, we can solve this one by trial and error method. But trial and error method, how we will start actually? If this is the H, then first of all at the beginning we can start with the embedment depth equal to the same depth and see the result of this, and accordingly seeing the value of net value plus or minus, you can decrease or increase, and finally, you will get a value where actually for a particular d naught it gives you close to 0, and that will be your depth of not depth of embedment d naught, and if you with d naught if you add y naught you will get the depth of embedment. So, this is the way, that means we have explained in this diagram what is what here, and then based on that we calculate coefficient 1 C 1, coefficient 2 C 2, coefficient 3 C 3 and coefficients 4 C 4, and then this equation can be used d naught to the power 4 plus C 1 d naught cube plus C 2 d naught square plus C 3 d naught plus C 4 equal to 0, and by this equation, a fourth order equation we are getting. This fourth order equation by trial and error method we can solve it to find out the d naught. Once you get the d naught, your d become d naught plus y naught. Okay. So, this is the way one can find depth of embedment, and now I will go to next slide. You can see here what I have shown here. This typically this type of retaining wall, always there will be water table, actually water table will be somewhere here, or it will be close to the surface anyhow, at least it will be in the dredge level, water will be there. So, because of that, if there is water table present, then how will be the analysis? What is the difference? Everything will be same. Actually, you can see only this pressure diagram will be changed, and how it will be changed? Wherever there is water table, below water table, wherever there is a gamma, gamma will be replaced by gamma submerged. So, accordingly it was something like this, now it is reduced here. So, similarly everywhere wherever there is gamma, you can replace by gamma submerged. Accordingly, this coordinate you will get here, 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 everywhere you will get coordinate, and that will be your final pressure diagram. And after getting that pressure diagram, you can again whatever notation I have given here, whatever notation I have given here, all can be kept unchanged, and again using those notations, again we can find out C 1, C 2, C 3 and C 4, and then finally you can find out d naught to the power plus C 1 d naught cube to this equation equal to 0, then you can find out again d naught. So, I have taken actually without water table, but if there is water table anywhere, what is the change? Only change in gamma will be replaced by gamma submerged below the water table. Rest of the calculations are same, calculation of C 1, C 2, C 3, C 4 all are same. Then finally, I express the equation fourth order equation and then solve for d naught, that is all. So, if there is water table, actually it will become complicated definitely. So, because of that I am not doing in terms of water table, I have considered in terms of without water table. Okay. So, if there is water table, this is the only change you have to take. Now, next slide, if you have suppose this is the one what I have done actually approximate a real rigorous analysis you have done based on the bending of the retaining wall, where it is becoming active, where it is becoming passive. Accordingly, pressure diagram I have changed and I have taken effect of all, but there is another method which actually simplified method, where actually we will not take all those complication. I will consider, since the wall this side soil is retained, I will consider the wall is tendency to have moved this side. So, this side I will consider active, and since the wall this side wall is pushing this side, I will consider this side is passive, entire passive, this is entire active. This is the way if I take, then your calculation will be very simple. So, based on this you can see here it is done. That means, if I do simplified method, that means this pressure and this pressure must be equal. If you want to do, if you do that, then you can get this equation, and then Pa is this and Pp is this and Pa is this. So, this if I substitute in this equation, then I will get this equation. I am getting this equation, and this equation if further if I expand, then I will get a equation, a cubic equation I will get. This is the cubic equation, and from this cubic equation you can see k d cube 3 k h, or I can further simplification can be done, d cube minus 3 k a over k h d h plus d minus k over k h cube. This is the way also can be expressed, otherwise this is also okay. So, that means what I have done, the sheet pile wall is, this is the sheet pile wall, entire wall assume this is moving this side. So, entire this side is active, and since wall is moving this side, so entire this side is passive. So, this passive force and this active force must be equal, that is the thing I have written here, and then express the P p, express P a, substitute this equation and then simplify, you will get this, and further expanding and express in terms of d cube, then you can get this is the equation. This is again a equation of cubic equation, you can solve it by trial and error for d, and that d if you compare with the rigorous analysis, you will see that they will not be very close, there will be some difference. Obviously, we can use a factor of safety to compensate that, and so this analysis sometime particularly for class examination, this method is more applicable for you. In fact, rigorous analysis I have shown, but in the exam you can expect only the simplified method, that means this is the method. So, if the wall height is given h, how to find out the d, assume depth of embedment d, then you can find out k active pressure on a wall height equal to h plus d, and passive pressure on a wall height of d, and then equate active pressure and passive pressure, simplify it and then express the equation in terms of d and then solve for d. That is the way, and that is actually important for exam. Rigorous analysis only for showing you I have done, but this is very difficult to do in the exam. So, I may not be important, but this is the one you can practice more. Next, actually I will show you, so that whatever I have told at the beginning, that sheet pile wall can be of different combination, that means above dredge level it is sand, above dredge level sand, and below dredge level this is actually cohesive. So, you can see phi 0 and it is having a value of C. So, in that case your pressure diagram will be, if it is no water table, it will be like this, and then it will go like this, and then this is again based on rigorous analysis. If I want to do simple analysis similar to that, simple diagram can be obtained, that your this side active and this side passive, and then equate and then find out the depth of embedment, that also can be done. But based on rigorous analysis, if the cohesionless soil above dredge level and cohesive soil below dredge level, this is the diagram, typical diagram. And again we can, the way I have done the for sand, same thing actually. First of all we can consider force equilibrium, then moment equilibrium, and then based on that we can again arrive at another equation and again solve for the equation for the depth of embedment. So, this is one. Next one is again I will show, this is another one, actually you can see that this is above dredge level also C soil, below dredge level also C soil. So, the typical pressure diagram will be something like this. Again similar way, the way I have done before, the pressure equilibrium, force equilibrium, then moment equilibrium, then formulate the equation and solve for D. So, that also can be done. So, I am not going in detail of these two part, only sand that case only I have discussed, both simplified and modified, and that may be enough for undergraduate. So, you can practice those. So, these are only thing I have shown that there can be other combination which is possible in the practice. Okay. With this I will stop here. Thank you.